All right, let's talk about how to solve complex circuits. Now, and really these aren't overly complex circuits. If I could, kind of an oxymoron, simple complex circuits is what we're talking about. Many times you won't have to go through all of these steps to try to figure out whatever answer is asked of you in a question. You can just use the simple series and parallel rules. In parallel, remember, voltage remains the same, current divides. In series, it's the voltage that splits up between the resistors, and the current stays the same. You often can just use those rules to get more directly to a specific answer. But if you have to find everything about a circuit, you're going to end up going through these rules right here. Now, when I say complex circuit, I mean something along these lines. Something that does not have a simple, hey, this is all in series or all in parallel sort of resistors. Because look, here are 3 resistors that might be in series, but here's something that might be parallel. You wouldn't want to combine those 2 in parallel first, by the way. Maybe all 3 of these are in parallel with that, because notice the current can divide between those 3. And then if all these are combined, are they in series with him? Are these guys in parallel? So those are things that we're going to talk about here in this unit. Now, first thing that you need to do, draw the original circuit, and oftentimes the schematic will already be drawn for you. Next, add the 2 most obvious resistors together, creating, or 2 or more, creating an equivalent resistor in their place, and redraw the entire circuit with it. So you're going to end up redrawing a number of circuits here, and you're going to see that in the example problem. Oftentimes, the most obvious things to do will always be on the furthest away from the battery, or the furthest outside, if you will, in the schematic. For example, here are 3 obvious resistors that are in series. You can't say these 2 are an obvious parallel, because what about these guys that are in between along that exact same wire? Work from the outside in. So here are 3 that are obviously in series, and those would be the first 3 that I would draw. Then, after you have added these together, get an equivalent resistance for them, redraw the circuit with their equivalent resistance in there. You are then going to continue to add the most obvious resistors 1 step at a time. So after I add these 3, and I'll put their equivalent resistance over here, then I can add their equivalent resistance to the 40, and come out with, through parallel, come out with an equivalent resistance, and so on down, continuing to add them 1 step at a time, generally working from the outside in. That's just a rule of thumb, I guess I should say. But the most obvious ones, the ones that you know you can't get wrong, working from the outside in, until you get to a very simple circuit, 1 resistor. Now that you're in a very simple circuit, you've worked 1 step at a time, redrawing the entire way, you're going to find the unknown in that simple circuit, which is generally speaking the current. Now that you have the current in that simple circuit, use your parallel and series rules to step back upwards, if you will, through the circuit drawing. So all of those different drawings that you have made, you're going to work back upwards through them, figuring out each thing for each resistor on that drawing. Continue to work all the way back up through the drawings until you figure out everything that you did not know. So worst case scenario, if you can't solve directly for something, you're not sure how to get there, just solve for everything in the circuit and you're guaranteed to get it right. One example problem here for you. I have a circuit, 10-volt battery, and then 4 resistors like this here. And I'm going to start out with the most obvious resistors, trying to add them all the way down to a simple circuit. Basically, I know the voltage of the battery, and I know the resistance of all these guys, but I don't know the voltage drop across each of them individually or the current through them. And so that's what I'm going to look for, the details that are going through each resistor here. Now, the most obvious one to add together are going to be these 2 parallels. They are the furthest outside away from the battery. These might feel like an obvious series, or these 3 might feel like an obvious series, but you can't say that because, check it out, the current actually has a chance to divide. It can come down this way, or it could come this way. So that you can't really say anything are in series there. In fact, if you see a node anywhere, like here and here, if you see nodes that are splitting up the resistors, that should be a big alarm bell there of I need to be extra careful. These might not be as obvious as I think. The 2 most obvious ones, because there's nobody in their way, there's no other resistors in here along those lines, these 2 in parallel. So I'm going to redraw my circuit, and I'm going to add these 2 in parallel. All right, so I'm going to smush these 2 together into 1 resistor, if you will, smushing R3 into R2 there. Adding them in parallel is going to give me some R, and I've got to figure out its resistance. Now, the equation to figure out equivalent resistance for parallel is 1 over R. Let's use this color here. 1 over R equals, and we'll call it RT, right? 1 over R1 plus 1 over R2. So now I can just plug in and solve. All right, so I solved for my equivalent resistance here. The combination of these two in parallel, they're the ones that are the most obvious, reducing them down to one resistor, the equivalent resistance for him. These two combined is 18.75 ohms, not rounding for sig figs until the very end. Now I combine the next most obvious ones. And here I've got, without any question, 3 that are in a nice easy series. Notice they're all in the same line. There is no division between them. There are no other branches going off anywhere with other nodes. They're just in a nice easy line. So I'm going to add those 3 in a series. All right, so now I've gotten all the way down to my simple circuit. I took these 3 resistors and added them all together to get one resistor now. They were the only 3 left, so now I only have one resistor, and their equivalent resistance of these 3 R came out, because they're all in series, to be 58.75 ohms. So now I have my simple circuit. My 10-volt battery still hasn't changed, right? I haven't done anything to my battery. All I did was add the resistors. So I took the 2 most obvious, added them together. Then looking at my next drawing, notice I'm redrawing each and every time. Then looking at my next drawing, I have 3 that are in an obvious series. So I add them together and I get my equivalent resistance on the final circuit, my equivalent circuit, 58.75. And the only unknown here is, what is the current I in this loop? So now I'm going to start working back upwards. I'm going to solve for the current in my simple circuit, and then I'm going to use that current or voltage, depending on which I need, and gradually work back up through this. So here, let's solve for current using Ohm's law. And once I use Ohm's law to solve for the unknown in this simple circuit, which was current, because I knew the voltage and I know the resistance in my one resistor simple circuit, didn't know the current, V equals IR, I get a current of 0.17021, and then I'm going to carry all those decimals as I go up, but just reporting it quickly, 0.17 amps. Now, I'm going to start working back upwards, trying to get back to the circuit, the original, with all the different resistors in there, figuring out the details. Now, whenever I work back up, if you will, taking this one resistor now and expanding it back to these 3 were in series. Whenever I expand them, I'm in series. Now, the rule for series states current remains the same and voltage divides up, which means the current inside of this loop is the same as in my other loop, 0.1702, so on, amps. That tells me the current across each one and leaves the unknown, or the current through each resistor, which leaves the unknown to be the voltage in each one. I don't know V here. I don't know the voltage across each of these resistors. So that's what I'm going to solve for using Ohm's law, because now I know the current through each one of them, 0.17, and I know each of their resistance. All right, so now I know the voltage drop across each individual resistor. This 20 ohm, this 18.75 ohm, which is actually representation, is the equivalent resistance of those two put together, remember, and this 20 ohm. So I actually did Ohm's law for each one of those to calculate the resistance. Now think back why I carried the current up. Remember, current in series stays the same. That's why I can use the current from the equivalent circuit up here for all of these, because they're in series. Also remember, voltage divides. So my 10-volt battery, it's going to divide all of its electrical potential difference across these 3 resistors, starting at 10 and then gradually dropping down to 0. But notice here, if I add these all up, 3.4 plus 3.2 plus 3.4 brings me back up to my 10 volts, so the voltage divided up between them. Now I just need to figure out these 2 resistors. I already know the details for these 2 resistors because they stay the exact same. But I'm going to have to take this one and split it up to these 2. So now the question is, this resistor that gets split into these 2 in my final circuit, these 2 are in parallel. What are the rules for parallel? Now, parallel, voltage remains the same, but current divides. So I'm going to take the voltage drop across him, and I'm going to split it up between those 2 resistors. All right, so notice I carried the voltage and the current from these two exactly the same up here because this 20 ohm is still the exact same and this 20 ohm is still the exact same. Nothing happened to this resistor. It's this equivalent resistor here that got broken apart into the parallel, and the thing that I can carry, the thing that remains the same, in parallel voltage remains the same. It's the current that is going to divide up, so I need to solve for the current in these two. All right, so I already knew the voltage and the current across them. I used Ohm's law for the 30 and the 50 coming from this equivalent resistor working. Just back up another drawing here to figure out the current between the two. The current through the 30 was 0.11 and the current through the 50 was 0.06. Amps. Notice that the addition of these two, because in parallel, voltage remains the same. That's why I was able to carry the voltage up from here to these two, right? In parallel, voltage remains the same, but the current divides. A current of 0.17 amps comes through here, and then 0.11 comes down here, and 0.06 comes down here. It splits up and then recombines after it comes through. So at this node, the 0.11 and the 0.06 recombine to give you, once again, a 0.17 amp current as it comes back around to the battery. Now I know everything about this circuit. I know the resistance, the voltage, and the current for each individual resistor. Notice that I had my drawing. I solved downwards, if you will, redrawing in each step, adding the most obvious resistors, all the way down to an equivalent resistance with a simple circuit. Then I used Ohm's law to solve for each unknown step by step. What did this turn into? It turned into 3 resistors in series. Thus, I carried my current because current remains the same in series. All right, here's another equivalent resistance. Carry that up. These two I already knew, so I just copied in their information. This turned into a parallel, and parallel voltage remains the same, so I can use Ohm's law to calculate the current for each of those. So now I know everything about my circuit.